Hello everyone. In today's lecture, we'll discuss about sorting algorithms in general and then selection sort algorithm. So it's quite often that we would like to arrange things or data in sorted order, in certain order maybe. It is to sometimes to improve the credibility of the data or to be able to search or extract the information quickly out of that data. For example, while playing cards, even though in our hand, if we have very less number of cards, we would like to uh, use these cards in sorted order, in increasing order of rank, or maybe in the order of suit, etc. Or while using a travel site, something like hotels.com, some number of hotels will be listed, but we would like to use it in sorted order. That is sorted according to star rating, according to guest rating, or according to price from high to low, low to high, etc. Or maybe while using an English dictionary, in a language dictionary, in that the words are given in the lexicographical sorted order. If the words in a dictionary are not in sorted order, then it's of no use, isn't it? Or something like a tabular data where, for example, a medal tally in Olympics. So here in these examples, we would like to use this data in sorted order, maybe for presenting it in a better fashion, or uh, maybe to understand it things better, or in order to in order to search things quickly out of the data, etc. So the definition of sorting is that sorting is arranging elements in a list or collection in increasing or decreasing order of some property. So you have a list or a collection of elements which we would like to arrange in increasing or decreasing order of some property. We know that the list should be homogeneous, or all the elements should be of the same type. So in order to study the sorting algorithms, we typically use a list of integers, and we normally write algorithms to sort the list of integers in the increasing order of the value. For example, to sort the list 2, 3, 9, 4, 6, the increasing order of value is 2, 3, 4, 6, 9. The decreasing order of value 9, 6, 4, 3, 2, or in the increasing order of the number of factors. So that's what we define the different order of the property. In this case, the property is the number of factors in the increasing order of number of factors. So 2 has got 2, 3, 9, 4, and 6. 2 has got 2 factors, 1 and 2. 3 has got 2 factors, 1 and 3. 9 has got 3 factors, 1, 3, and 9, etc. Looking at an example of the list of strings, for example, fork, knife, mouse, screen, and key, they can be sorted in the lexicographical order or as they appear in the dictionary. Or if you have some complex type object like a student object or a hotel object, they can be sorted based on different properties. For example, a student object, it has data like roll number, name, address, then some sort of marks, etc. Then this object can be sorted based on any property that is available in that object, maybe based on roll number or name, etc. So sorting is not only gives you better representation of the data, it's also important in case of searching for a particular element in the data, or extracting some information from that data. For example, if you have an unsorted data, you can only perform linear search in that data. So, but if you have a sorted data, you can perform binary search on top of that data. If you perform linear search and if you have n elements in the data, you need to do n comparisons. That is the linear search of time complexity order of n. So, for example, if you have n is equal to 2 raised to 64, so and each of the comparison is taking 1 millisecond, then it takes 2 raised to 64 milliseconds. 2 raised to 64 milliseconds will account to maybe some number of years. But if you have that same data in sorted order, that is 2 raised to 64 data, you can do the search and search for a particular element in that data in just 64 milliseconds, because the binary search takes only order of log n time. So 2 raised to, sorry, log 2 raised to 64 to the base 2 is 64. We have many different types of sorting algorithms, like we'll be talking about bubble sort, selection sort, insertion sort, merge sort, quick sort, heap sort, counting sort, radix sort, etc. And each of these sorting algorithms are developed in time, and uh, maybe because of the uh, time complexity, or because of the some property of the algorithm, the other algorithm has come and it replaced the other algorithm, or maybe because of the type of the data or the size of the data, etc., other algorithms has been developed. We'll be talking about each of these algorithms in detail. Classification of sorting algorithms, we would like to classify these algorithms based on some of the parameters, or we would like to analyze these algorithms based on these parameters. The first parameter we would like to take is the time complexity of the algorithm, the rate of growth of time taken by the algorithm with respect to the input size. We have already discussed about the time complexity of the algorithms in the previous class. So we know that some of the algorithms are relatively faster than the others. So you can see that some of the sorting algorithms are going to take order of n square time, and some others are taking going to take order of n log n time, which is very good compared to order of n square, which is a slow sorting algorithm. The second parameter we would like to talk upon is space complexity, which is memory usage. Uh, there are sorting algorithms which we call in-place sorting. They use constant amount of extra memory to rearrange the elements in the list. So sorting is just a rearrangement of elements in a list. So if you're doing it in place, they don't require any extra amount of storage memory, extra amount of memory. Some other sorting algorithms like merge sort actually uses extra memory to temporarily store data. Uh, so in that case, the memory usage grows with input size. So space complexity is the second parameter we would like to uh, discuss the analysis on different sorting algorithms. Stability, a stable sorting algorithm in case of equality of key, if both the elements having same key, then the elements that was coming before in the original list, that will also come before in the sorted list. And that sort of an algorithm, that sort of a sorting algorithm is called a stable sorting algorithm. For example, uh, let's say this is our original list and we would like to sort these four numbers, 6, 9, 3, and 6. The sorted list is 3, 6, 6, and 9. Here we have two sixes. First one is this, and the second one is this. And in the sorted list, the second six that was coming, that was appeared in the original list, that has come first, and this six has come after that. Then this algorithm that was produced, this output is not a not a stable sorted algorithm. Sorting algorithm. So if it is a stable sorting algorithm, then the output should be this three, this six, then the six of hearts, and then nine. So in this case, in the original list, the six of clubs was coming first, and then the six of hearts. So in the sorted list also, six of clubs should first come first, and six of hearts should come next. Then that sort of a sorting algorithm, that is the key, that is the element that is coming before in the original list, that should come in the that should come first in the sorted list rules. So that sort of a sorting algorithm is called a stable sorting algorithm. Another classification is internal or external sorting. When all the records that are needed to be sorted are in the main memory or RAM, then such a sorting algorithm is called an internal sort. If the records are somewhere in auxiliary storage or like disk or tape, then it is called an external sort. Some of the sort algorithms are external sort, like radix sort. Some sorting algorithms are recursive, some other are non-recursive, like quick sort, merge sort are recursive algorithms, while insertion, selection sort, etc., bubble sort are non-recursive algorithms. So these are the five parameters we would like to analyze, or we would like to classify the sorting algorithm. Based on these parameters, we would like to classify the sorting algorithm. Okay, so next we will discuss about the selection sort algorithm. So let's say we have a set of cards and we want to arrange these cards in the increasing order of rank. Uh, what we do is, in selection sort, and selection sort is the most basic, or uh, this is how common people do sorting. uh, we will see the selection sort first with this cards example, then we will use uh, a list of integers for sorting using selection sort. So how we do it is, we keep all the cards in the left hand. This is your left hand, and we keep all the cards in the left hand. Then select the minimum. The minimum here is 3 out of these cards, and move it to the right hand. Then we are left with only three cards, 9, 6, and 4 in our left hand. Then once again we select the minimum out of these cards, and we repeat this process until the left hand is empty. For example, in this case, 3 is selected and 3 moved on to the right hand. Then what is left is 9, 6, and 4. Then 4 is your minimum card in the left hand. Select that and place it after 3. So 3 and 4. Then you select the minimum 6. 6 will be passed on to the right hand. Then you have 9. 9 will be passed on to the right hand. Now your left hand is empty, so your sorting is complete. So this is how common people do sorting, or this is the most basic sort of sorting algorithm. We call it selection sort. Let's do it with a simple integer array. The same method, or the same method which we have adopted in the case of playing cards, we do it with an integer array. We have six integers stored in indexes 0, 1, 2, 3, 4, and 5. The values are 2, 7, 4, 1, 5, 3. So what we do is we use this as our base array, and we create a new array. So something like this is your left hand and this is your right hand. So you create a new array with the same size, uh, and from the first array you select the minimum element and move it to the right hand side, or move it to the other array. Now you should mark this minimum element not to be used because this is already considered. Now once again you select the next minimum element. I have marked it with green color because that is this element need not be considered again. Programmatically, you can do it like you can replace this number with some large integer. For example, some large integer, so that at any particular point of time you will not be selecting. Uh, while calling the minimum value, you will not be selecting this, or else you can write it as an integer which is not part of your array. You are sure which you are sure that it will not come as an element in your array. So the next minimum is 2, that is moved on to the array. You select the next minimum and move on to the your new array. You select the next minimum, you move on to the array. You select the next minimum, it is 5, that you send on to the array, the new array. You select the next minimum, 7. Now all your elements are done, and in the right hand side or in the new array you got it all elements in the sorted order. So here you can see that this sort of sorting algorithm requires an extra memory which is equal to the size of the original list. That is, we had six elements with integers 0, 1, 2, 3, 4, and 5, and we require the same size here. So, if this list is very large, then it will be difficult, and which is almost equal to the size of your memory. Then you may not be able to do it with using selections. This particular set of type of sorting algorithm. So, what we have discussed just now is not an in-place sorting algorithm, but we can convert this into an in-place sorting algorithms, the selection sort in-place sorting algorithm. Let's take the same list of integers again. In this case, the algorithm proceeds like this. You select the minimum element, then instead of inserting that element, instead of placing that element onto a new array, you will be placing that element onto the same array. That is, in this case, for example, the minimum element that you're going to select is this one. Then what we do is you just swap the elements at this position, that is 1, and at 0th position. We know that this is the minimum element and this should come at the 0th position. So what we do is we'll be just swapping 1 and 2. So 1 will come here and 2 will come here. So 1 is your minimum element. Okay, so now you just swap these two elements. So before this is your minimum element 1. Now you will be swapping the element at zeroth position. At any round, you will be swapping element at zeroth position and the minimum element. So one will be sent here, two will be sent here. The next step, you will be finding the next minimum and you will be swapping it with the element at first position, that is element at this position. So one will be these two elements have been swapped. Next element, the next minimum element is 2. So you will be swapping this element and the element at the position 1. This position is already, the element at this position is already fixed. There is no need to uh, compare it again. So 2 and 7 is swapped. Then the next minimum element is 3. So it should be swapped with the position at this position 4. So 3 and 4 is swapped. Then the next minimum element is 4. 4 and 7 need to be swapped. 4 and 7 is swapped. The next minimum element is 5. So it is in the correct position. So there is no need to swap it. Then the next minimum is 7. It is also in the correct position. There is no need to do anything. So once all the elements have been considered like this, then you can stop, or you need to do this in n rounds or n minus one round. Next, we will look at the selection sort algorithm. Just now, we have done it, the selection sort algorithm. That is, we are passing an array A, which is this, and n, the number of elements in the array, to this function. Then this loop for I equal to 0, I less than n minus 1, I plus plus. This loop is for running through the array n minus 1 times, because the last step that is not required, because uh, at any iteration using this value I, we will be trying to find out the minimum element. Once we identify the minimum element, we'll be swapping it with the position. So at I equal to 0, we will be finding the minimum element and we'll be swapping it with the minimum position. So initially we keep it as I minimum is equal to I. Then we take one more loop for j equal to I plus 1, j less than n, j plus plus. Then we'll compare a of I and, sorry, a of I minimum and a of j. If at any position a of j is less than a of I minimum, then update the I minimum index. So for example, at any position, you keep it as I minimum equal to 0 and you compare through it. At this stage, let's say you got the index 4 as having value less than this, then we'll keep it as this as the new minimum value. Once you have gone through the entire array, then you will get it as this is your I minimum value and this is your I value. So I minimum and I will be swapped. So you will be swapping these two values. So at any iteration, it's a very simple sorting algorithm. At any iteration, uh, at the iteration 0, you will be swapping the minimum value with the zeroth index. At the iteration 1, you will be swapping with the next minimum value with the index 1, next minimum value with the index 2, and so on. And you will be running this the number of iterations will be to n minus 1, because the last index anyway that will be in the minimum value. There is no need to compare it with any other values. So that is selection sort algorithm. We'll just quickly do analysis of the selection sort algorithm as well. Selection sort algorithm is the time complexity of the algorithm. It's a slow sorting algorithm. It's an order of n square algorithm. So let's say this is a for loop running through 0 to n minus 1. So this instruction I minimum equal to I will be executed n number of times, or n minus 1 number of times. Sorry, 0 to n minus 1, n number of times. Whatever linear in n. And once again, we take one more loop for j equal to I plus 1 to j less than n. And this if statement also will be executing this into n into n minus 1 number of times. So in the first step, this will be n minus 1 times. Then in the next step, this will be executed n minus 2 times, then n minus 3 times, etc. So you sum over all the number of times this statements are getting executed. Then you will get it as a polynomial of degree 2. So time complexity will be taken as the maximum degree of the polynomial. So it is order of n square. The space complexity of the algorithm, just now we have discussed an in-place sorting algorithm. There is no additional space requirement. We require only few variables like I minimum, I, j, etc., which are actually constant, which are going to take constant uh, space. So we say the time cost space complexity of the algorithm is order of 1. The stability of the algorithm, selection sort is not a stable sorting algorithm. Selection sort is an internal sorting algorithm, and this is a non-recursive sorting algorithm. So that's all about selection sort. In the next class, we'll come up with bubble sort and internal sort. Thank you.